So now that we've talked about all of the limits that can be found relatively straightforward and air quotes easily, we want to talk about special trig functions. But before we can talk about some special trig functions that will be that will be very, very handy, we need to talk about how we got there and how it's proven, how they're proven. So we're going to talk a little bit about the squeeze theorem. Now, this is a theorem, it's been proven. We won't prove it at the high school level, but I can certainly kind of sketch out a picture for you to make sense of the concept that's being used when I prove one of the special trig functions later in the video. So here's what we're looking at. A case where we want to evaluate a function at x equals 1. We know there's a hole, but we don't have anything to talk about that function about. We have no parent formula, we have no direct calculations that can be made on whatever that function is. We don't really know much about it, but we do want to be able to evaluate it at x equals 1. If we can find a function that we know is always bigger than f, so let's call that g. If we can find a function that's always bigger and we know shares the same property at the input of x equals 1, and then if we could find another function that we know is always smaller, let's call that h of x, but shares the same properties at the input of x equals 1, then we can use the squeezing logic and say, well, since g of x is always bigger and approaches whatever L is, and because h of x is always smaller and approaches the exact same L value, then f of x, because by logic we know is between the two, by the squeezing theorem we can say that f of x equals L at x equals 1. So let's use this idea to talk about and to prove a very important trigonometric limit. So the limit as x values approach 0 of sine, and I'm going to use the variable theta this time, over theta equals 1. So if I'm going to use the variable theta, I have to use it all the way across. So if theta, so the limit as theta in radians approaches 0 of sine theta over theta. Well, sine theta we don't have any trouble with because that's just 0. But 0 in the theta in the denominator we have total bits of trouble with, because as theta values approach 0, the limit approaches something that's undefined, and we want to actually show that this value is 1. And if you graph this, you see that indeed it appears to be true. So let's use the squeeze theorem and sort of build up the case. All right, so I've set up a picture here to start the process. You won't be expected to make this proof, but you will be asked at some point to describe the process used to prove that the limit as theta approaches 0 of sine theta over theta does indeed equal 1. So pay attention to what I'm doing, though you won't have to reproduce the proof on your own. So I've set up a triangle. At this point it's just a bunch of shapes for you, but the important pieces of information are that we're looking at the unit circle, so I have the coordinate 1, 0, which is an intersection of all parts of this diagram. And that if that's true, that I have 1, 0, then I could label this point using trig values as 1 and tan theta, taking advantage of the fact that tan theta equals y over x, and in this case x equals 1, so tan theta equals whatever y is, and that's exactly what I'm trying to get here, is that this y value would lead to the coordinate 1 tan theta. And by the same logic, I could call the coordinates for this point cos theta, because on the unit circle cosine theta is the same as x over r, but r equals 1. So I could call the x-ordinate cosine theta and the y-ordinate sine theta. So now let's distinguish between two triangles that exist here. I have the triangle inside, and then I have the triangle outside. Right? So I can definitely say that the outer triangle, the lime green one, and let's just sketch it up right here. The lime green triangle is definitely, I want to work in the other direction for reasons that will become clearer later. So the lime green triangle is definitely bigger than the purple triangle. Now they're not similar triangles because the lime green triangle is a right angle and the purple triangle inside is not. But it's pretty obvious that the area of the purple triangle in here is clearly smaller than the area of the entire contained right triangle. And it's also true that the sector, the area of the sector, because you can see that the curve falls right between the two triangles, that the area of the sector is greater than, or excuse me, the area of the sector is less than or equal to the right triangle, and it is also greater than or equal to the purple triangle. Alright, so that's just using pictures and logic to see that indeed I have set up an inequality that you can imagine a squeeze, right? So if I can find somehow, if I can somehow convert the area of the sector to look like this function, then I can use the fact that the purple triangle is smaller and the green triangle is bigger to, in the squeeze theorem, hopefully to show that they all equal the same thing, which is 1 at this value. I mean at theta equals 0. So what I need now is expressions for each of the areas. Well, the area of the green triangle would be tan theta over 2. And I chose that, right? Because I'm looking at the height. We know that the area of a triangle is its height times its base divided by 2. Well, the height of this triangle is tan theta. The base of the triangle is 1, the x input, 1, and divided by 2. So for the purple triangle then, now I'm dealing with the height being this coordinate, cosine sine, so I can set up that sine theta over also over 2, because the height of this triangle is indeed sine theta, that's the y-ordinate, right? And the base of that triangle is the same 1, so height times 1 divided by 2, done. Now all I need is an expression for the sector, and that would be theta divided by 2. Now all I have to do is algebraic manipulations to convert the area of the sector to the function that we want it to look like. So I'm going to multiply all three elements by 2 over sine theta. Alright, so my 2's cancel in the center and I have theta over sine theta, which is just the inverse of what I really want. That's nice, or the reciprocal of what I really want. Here at the end, I can cancel my 2's, I can cancel my sine thetas, and so here I have 1 is greater than or equal to theta over sine theta, which is, 1, which is less than or equal to theta over sine theta, which is in turn less than or equal to, well, what does this equal? Well, certainly my 2's cancel, and tan theta is really just, let me write it down here, tan theta over sine theta. I'm really looking at sine theta over cos theta times sine theta. or 1 over sine theta, I should say, because sine's in the denominator. These cancel, and I'm left with 1 over cos theta. So now I can take the inverse of everything. I could do a whole bunch of algebra and show that it's true, but I'm going to ask you at this point to do the algebra on your own to verify what I'm saying. But now if we take the reciprocal of all the components, it'll change the signs. And now all I have to do is evaluate what is the cos of, what's the limit as theta values approach 0 of the cos of theta, and what is the limit as theta values approach 0 of 1, and then hopefully they will equal the same thing, and it'll tell us the value of sine theta. So by direct substitution, well, this is the cos of 0, but we know the cos of 0 just equals 1, which is going to be less than or equal to sine theta over theta. I guess I could have written it here as well. And that'll be less than or equal to, well, this is just a constant function, so it equals 1. Since we know that we set up a situation where this value is always, or the function that led to this limit is always smaller than sine theta over theta, and that the value of this limit is always greater than sine theta over theta, we can say, therefore, the limit as theta values approach 0 of sine theta over theta equals 1. And using these results, we have our second special trig limit, which is the limit as theta approaches 0 of 1 minus cos x over x equals 0. And I'm going to rewrite, let's move this over here, give us a little screen to work with, and I'm going to rewrite the sine function without theta notation. I use that just for the proof, and so I want to write it the way we want to memorize it, which is the limit as x values approach 0. Good Lord, I've mixed them all up. There we go. As x values approach 0 of sine x over x equals 1. These are just true statements proven by the squeezing theorem, and we're going to use it now to work a problem. So find the limit as x approaches 0 of the, excuse me, wrong page, of tan x over x. Okay, so in this case, I want to make it look like one of these. So I need cosines or sines. I don't know which one I'm going to end up with, but let's go ahead and rewrite tangent in sines and cosines and see if I can do some kind of a cancellation thing. So that'll give me the limit as x approaches 0 of sine x over cos x over x. Well, that's really just the same thing as the limit. Oh, and I'm going to do this in 2 steps just to make sure everybody sees it really clearly. Of sine x over cos x, and if I multiply by the reciprocal of the denominator, I get an x in the denominator. So now I can see my sine x over x and rewrite this limit as x values approach 0 of sine x over x times 1 over cos x. And we know from properties that we learned in the previous video that that's the limit as x values approach 0 of sine x over x evaluated separately than the limit as x approaches 0 of 1 over cos x. And our hope and our prayer is that we don't have a problem with the second limit, because we know the first limit, this one, equals 1. We just proved that. Times, well, 1 over the cos of 0 by direct substitution, looking a lot like a theta. Well, the cosine of 0 is just 1. So this whole original limit equals 1.